Hello and welcome to the talk on the advantages of isogeometric B-Rep analysis for the parametric design of lightweight structures. My name is Ann-Kathrin Goldbach and I am a member of the research group developing CAD-integrated design and analysis for lightweight structures at the Chair of Structural Analysis in Munich, alongside Anna Bauer and Professor Kai-Uwe Bletzinger, who are the co-authors. The shapes of lightweight structures are mostly characterized by very wide spans built by very small cross-sections. They are mechanically motivated with a strong interaction of form and force that needs to be considered by all analysis steps. The design and analysis of lightweight structures requires a complex iterative process accounting for non-linearities in the material modeling, shape generation, structural behavior, and also the construction process. This presentation shows the unified workflow for lightweight structures with the isogeometric B-Rep analysis. The presented methods are accessible through a plugin for Rhino and Grasshopper, which we called Kiwi 3D. A CAD model is typically stored as a B-Rep model and defined by NURBS functions. And by using these definitions for the analysis model as well, the so-called CAD-integrated analysis is possible. Isogeometric analysis is an appropriate approach and the key technique to model the interaction of form and force, because of several reasons. Firstly, continuous basis functions for smooth shapes in every step of the design chain avoid the transformation by meshing and backmapping. Secondly, refinement, i.e. adding more degrees of freedom to a geometry, is possible at every stage without changing the geometry or the parameter space. And the parameter space can be used for linking the material points of different stages, even if different discretizations are used. Weak coupling is possible without matching discretizations. And if the interfaces between computational design and computational engineering are kept smooth by keeping the same parameterization, not only from design to simulation but also the other way around, further simulations can be added in a modular concept. The iterative design of lightweight structures often requires parameter changes and updates. If geometric and mechanical model properties are parameterized in the model, the engineers and designers get the chance to explore these parameter changes in a very fast and efficient way. In the unified approach that is presented here, the design steps are linked and thus all design updates can be forwarded from one analysis to the next one. The hybrid dome was constructed in order to illustrate a number of typical consecutive design steps in lightweight design and analysis. It is built by 2 connected arches in the middle and 4 arches creating openings to all sides that are then covered with a membrane. A few typical parameters were chosen here. For example, the beams cross-sections and Young's modulus, the initial length, the support positions and the rotating angle. And for the membrane, the thickness, pre-stress, Young's modulus, and number of pattern stripes were considered. In the first step, the active bending of the rods needs to be analyzed. There are 2 approaches to this. One is a geometrically nonlinear analysis that was applied for the inner arches, and they are left to move to the equilibrium shape from an arbitrary reference one, in this case from a sphere. The outer beams were deformed from initially straight ones that were pulled into the final support conditions with contracting cables. In between these actively bent beams, the initial shape for the form finding of the membrane was defined in computer-aided design. Then, form finding was performed in 2 steps. First, the edge supports were regarded as fixed supports so that the membrane gets an initial equilibrium shape with the pre-stress. And once this equilibrium surface shape was found, a second form finding was performed with the edge beams as elastic supports. And once this form-found hybrid structure is generated, it could be linked to further analysis steps. With all these steps, the deformed geometry is available as a full CAD model that can then be taken as the input for the next analysis. So once the equilibrium shape was found, structural analysis for significant load cases could be performed. And since we are still within the CAD environment, the properties like curvature can just be analyzed by CAD functionalities and then be interpreted for the safety of the membrane with respect to ponding and fluttering, for example. In the next step, the cutting pattern generation was calculated. For this, the membrane shape was separated along geodesic lines, cutting pattern generation was performed, and finally, a mounting analysis could also be done. The mounting analysis shows the deviation of the erected structure from the form-found one with respect to shape and stress state, and thus helps to conclude on the pattern geometry. We can imagine that now changing the position of the seam lines or the number of stripes, which is a parameter of this model, changes the cutting pattern and consequently also the mounting analysis. And since all these analysis steps are linked, it is easy for the designer to explore the changes and see the effects on the resulting shape. Recent developments in the extended CAD environment facilitate the inclusion of external optimization loops to the decisive model parameters. The hybrid dome was optimized such that a predefined box should fit under the membrane roof. A genetic zero-order optimization was used, which is provided by Galapagos and Grasshopper for this task. Finally, the resulting shape would look like this. With CAD-integrated parametric design and analysis, lightweight structures can be modeled under consideration of their key features. Complex shapes built from extremely slender structural elements with highly nonlinear behavior. Staged construction can be optimally considered through the preservation of the analysis model throughout consecutive design steps. Furthermore, optimization loops can easily be added at any design step within the CAD environment and help designers and engineers to implement design requirements. Thank you for watching this presentation, and I'm looking forward to the discussion.